My name is David Katz. Thanks for joining our meetup. I'm going to talk about the autoencoder and its usefulness in anomaly detection. The topics are really just going to be, I'm going to go over what is an autoencoder and how do you use it for anomaly detection, some of the software tools that are available, and then I'll go into my demo, which will also include some information on setup, which fortunately is quite simple. Our hope is that you'll go to the community site, download this DXP, and try it on your own data. So what is an autoencoder? It's a deep learning network which attempts to create an identity transformation, but it does so with constraints. So if you look at the lower right, we have the schematic diagram where we have the input on the left, the output on the right. We're trying to encode the information into a smaller number of nodes or features, which is very analogous to principal components, where you would normally take the largest few principal components and say that that's most of the variation in your data, and then the smaller components are noise. But here, what we're really doing is, once we reproduce the input, we're looking for the mismatches, the imperfections in how that has been done. And that gives you a quantity that's called the reconstruction error. It basically says how anomalous are these data points. And you can look at that by component or overall or by sample. Just a quick look at some of the tools that are out there for doing that. We in this DXP Spotfire template, we're using H2O deep learning, which is very approachable. It enables you to just stack layers, so it's fairly simple, and there's just a few choices for the type of layers that you have. One of the advantages of the other family on the right under Keras is that it can leverage the GPU very well. I've grouped these together because Keras is one package that enables you to use the same front end, and then for performance purposes, you might use different systems on the back end. And all of those on the right have the advantage not only of the GPU, but you can specify more complex network topologies, but the learning curve is a little steeper. One thing that H2O does very nicely is work with sparse data, which if you're working with text data, for example, is very sparse. And actually, GPU doesn't work as well as the H2O. I also just very briefly mentioned the Deep Water project, which you might hear about, but it's mostly been abandoned in favor of Keras for that type of problem. So TIBCO has looked at a lot of these and created demos and accelerators using different TIBCO products. The one we're going to show today is this first one, and its strength is its very complete ability to do post-processing in a graphical way. There's also a Python-based demo in Spotfire using the Python data function, and also using TensorFlow. So you can also take a look at that on the community site. At the bottom, you have a link to the community site with a single page that sends you to all our anomaly detection demos. We also have the AWS Marketplace offers one of our packages that uses TensorFlow in connection with SageMaker. It has the advantages already set up to run on clusters, and is definitely worth a look. So what is the problem? Let's look at the problem that we're trying to solve. We have a lot of time series from different aspects of our process. Usually I think of this as a factory with a lot of sensors. That's a good application. But anytime you have multivariate time series, you can use this kind of technique. And again, like K-means, the way Tomas presented, this is unsupervised, right? We don't necessarily have labels or not very many labels. So the very traditional way is to look at one time series at a time and say, oh, this has gone out of the normal range by looking at the variance of what has come before. Here we take a cross-sectional approach. So for the analysis that we do, we have these vectors corresponding to individual points. And then the very important time dimension is added in the post-processing. And you'll see how that's done. So let me switch over to the live demo. And this is what you'll see if you download the demo from the community site, or the template from the community site. And it's showing here in Spotfire 10. You can also use it in earlier versions of Spotfire. It'll look a little different. As you can see, Spotfire 10 has the pages or tabs along the bottom. You've got the just a little introductory information about autoencoders. And then the setup is actually pretty simple. You just have to make sure that these packages are available to R. And so what you do is go to Tools, which I can't see because Zoom is on top of me. We go to Tools, Tear Tools, and this enables us to go to Package Management. And what it does is it retrieves what is already installed and also gives you this list. But I always just use the default. It's not really necessary to localize for most of us, although sometimes that gives you better performance. And then you have all the packages that are available. You have a search bar, and you just need to go through these four and install each one of them. So that's already been done. But I just wanted to show you that to make your path easier when you go to try this yourself. The next step is to import your own data. Now, I've got sample data in here, and you might want to take a look at that. But most of you will be most interested in loading in your own data, and that's done with replace data table. Now, in previous versions of Spotfire, that's just a menu option, file, replace data table. Right now, it's part of this data canvas, which Michael showed before, but it's got all the tables available and the ability to replace one of them here. So the user table is the one where you would replace it in order to use your own data. And when you choose that, of course, you get database connections, or you got local files that you can look at. So any tabular data can come in here either through one of these connectors or as a local file. And once you've done that, we close up the canvas and take a look at that data. This page is really here for free exploration of the data with any of Spotfire's visualization or analytics tools. But then we get more focused on selecting data for the analysis we want to do. So here, via marking, I've selected a slice of data that represents one factory and one product, and that helps in our time series. It makes sense to look at those one at a time. So then we register that data, basically use this button here to ingest the data. And then there's the step where we define 3 samples. So like in many data analysis tasks, we have a training data, we have a validation sample, and a test sample. Here we do something just a little bit different in that we do it in a time-based manner. So in order to start fresh with the new data that we've put in, we summarize using the time column, the date time column that we select. If there are multiple ones, there'll be a drop down here. In this case, we just had the one. And then we do this based on time intervals. And the reason for that is to prevent overfitting. If you did a random sample, then anomalies in the training sample and the test sample, the validation sample, they'd all show up pretty much as normal elements of this data. But if you wanted to generalize from a training sample, which you can identify this way, and then just by marking, you can identify a validation sample, and optionally, you can have a test sample as well. That actually works better with this kind of time series analysis for anomaly detection. Then, you know, we have whatever data that you've ingested and marked for analysis. We get a nice summary of them, and we have the ability to include or exclude them, or in some cases, we would change the data type, and that's done with this interface here. It's very straightforward to use. And then we'd like to actually go and build a model. And that we have a number of basic parameters that control the building of the model. So the model path is simply where you would write the output to save it for later. The epochs are, you know, how long do you train? How many times do you go through the data in your training process? And the hidden layers, this is the way H2O looks for your stack of layers. So we've got 25 input layers and 5 hidden, you know, 5 constriction type hidden layer, and then 25 back to restore or reconstruct the data. And this reflects that sideways hourglass that we saw before. And you can put in any number of these layers. Typically, you want a number that's somewhat larger than your actual inputs. Here, you know, we've selected a dozen or so inputs, so we put in 25. And then I'd say mostly this activation function is should be left at this setting, but you do have these different options of the technical side of building deep learning models. And the learning rate is a good one to adjust so that it's not too small, which would make things very slow, but if it's too large, you tend to not get as good convergence as you would otherwise. So here you can create the model, and you have a couple of diagnostic plots, which can be very useful. This is validation error plotted against the amount of training you've done, and that's extremely important. What you want to see is this kind of pattern where you get a tighter and tighter fit, but eventually you get overfitting, so the error increases. H2O is very nice. It will remember your minimum and use that for the subsequent calculations. Now, we talked about the reconstruction error. So here's a distribution bar chart of the reconstruction error, and we see that mostly you have a small reconstruction error, but at a certain point there are a number of cases which are potentially anomalies because we can't reconstruct them very well. So now we look at this in a time series context. So here is our training sample, and we also can look at the validation and test. And we have these sliders, so you can look at it. The thing that I found really interesting about this is that in most cases, you don't have isolated points in time where there's a problem or an anomaly. The anomaly tends to build up and last for a while and then resolve either by intervention or for some other reason. So I like to think of these as incidents. So if I mark this incident here, I get the variable importance, which is actually the contribution to the reconstruction error by each of your input variables. So here we see, you know, even though there are a lot of variables, the ones that really contribute a lot to this particular incident are these top 2 or 3. And by selecting this, we can get time series broken down to either the raw data or the contribution from this selected column, and again, the overall, which is just reproducing this one for reference. So you have a 3-part view of what makes this set of points over here anomalous. So the next step you can do is to say, well, some of these anomalies may happen more than once. If we have a lot of anomalies in our data, maybe it makes sense to cluster them. So first of all, we want to work with these incidents. So programmatically, we can set our threshold, and then beyond that threshold, we can say, you know, do we exceed that threshold over time? You know, for a minimum number of time, kind of like a Western electric rule. So then we can, you know, if we have enough anomalies to make it worthwhile, we can think about clustering. And here's the elbow plot. That is one way that you can decide how many different clusters you want to have, and then look at the k-means output. So here's all our inputs that we want to look at. And here are the 5 groups that we formed, the clusters that we formed. And you see that this is one way to visualize the profiles. Finally, we have the ability to take these clusters and maybe look at those over time. So here's the time series. Each point here represents one of these incidents, and we see that some periods of time have a lot of a single type of incidents, and then maybe over here we have a different group.